Welcome you all in my next lecture. So in my last lecture I talked about the notion of iterated integrals, and then Fubini's theorem I talked about, and then Fubini's theorem says that when double integral and iterated integral they are same, and we have two versions of Fubini's theorem that we have seen. Then I defined the notion of Riemann integral or double integral on arbitrary bounded region. Then I said that if I have a bounded region, then you just cover it by a bounded rectangle, which is possible because you started with a bounded region, and define a new function f two del which is exactly equal to that functions over that region d, and otherwise it is 0. And if your new functions f two del, if it is double integral suppose exist on the bounded rectangular region, then this I am defining the double integral of my f over the bounded region d is same as double integral of my newly defined function f two del over the bounded rectangular region R. And then I said that okay, if your domain D which is actually bounded, but if it is safe, you do not know the proper shape, then sometimes it is very difficult to calculate double integral and iterated integral. Then I started kind of discussing that okay, instead of arbitrary bounded domain, if I have very like a couple of domains which is simple domain like vertically simple or horizontally simple, then can I calculate what is called double integral or iterated integral. So that's maybe I will talk about more on that vertically simple or horizontally simple domain, and I will see whether I can calculate my double integral and iterated integral or not. Then I will talk about what is called change of variables for double integral, and then at the end I will talk about applications. Okay, so now I think I should start. Of course, this already I have discussed in my last lecture, vertically simple. I think I should start from once again. So vertically simple, as I said, it is a special type of domain, certainly which is not rectangular. However, so what I am doing, so I am saying that it is a domain in R2, and what about the properties? So x is running in the interval closed interval a to b, that is fixed. But y is running from one curve to another curve. So y is running between g1x to g2x, where g1, g2 are two continuous functions on closed interval ab and satisfying g1x lesser equal to g2x. So if these things happen, then this sort of domains I will say that this is vertically simple or type 1 region or y simple region. Two examples I have given. So that means x is running from a to b and y is running from this. Similarly, you have this region, another region, x is running, this is x is fixed a to b, and y is running from g1x to g2x. Okay. So therefore, if we have a domain which has this kind of properties, then I will say that it is a vertically simple type 1 on y simple region. Now you can easily talk about, like by symmetry, you can say that okay, if I instead of keeping x variable fixed in the interval ab and y varies from g1x to g2x, if I suppose keep y variable fixed in the interval c to d, and suppose x varies from say h1y to h2y, so I think that sort of domain we can also talk about. Answer is yes, you can also talk about those sort of domains is called what is called horizontally simple. What is that? Okay. So this is called horizontally simple domain. In that case, what will happen? Your y is fixed, y is running from c to d, but x is varies from left hand from h1y to h2y, that means one curve to another curve. So that means y is c to d, that means y, this is y is fixed, right, in the interval c to d. X varies from one curve to another curve, that means x varies from h1y to h2y, where h1y and h2y are continuous functions, and you will have these properties h1y is lesser equal to h2y. So that means y is varies from c to d, x varies from this to this, okay, this time. This is called horizontally simple type 2 or x simple regions. Similarly, look at here, this is y is fixed from c to d, but y varies from h1y to h2y. So that means y varies from this. This is called horizontally simple. Next is that if I have a region which is both type 1 and type 2, that means both vertically simple and horizontally simple. Answer is yes, yes. So look at this region, simple regions which is both type 1 and type 2. So that means look at this region. Okay. So I just, what is my definition for simple region? I am saying that if a region is both vertically simple and horizontally simple, then it is called a simple region. And you can, from the picture it is quite clear. Why? Because you see, so this is if x is fixed in the interval a to b, so x is fixed running from a to b, and y should run from where to where? g1x to g2x. So okay, so that means this is the one, g1x to g2x. So this is g1x, this is g2x. So that means it is actually vertically simple. And also you can think about same, because it is actually symmetry kind of things. That means now you keep y variable fixed from c to d. Okay. So that means x should varies from h1y to hy, and it is indeed the case. So this is so therefore this domain is actually vertically simple as well as horizontally simple. So this is kind of domain is called simple regions. Okay. Some example, of course, I said that some example which is not vertically simple or not horizontally simple. So for example, these are the domains. This is actually stands for what is called vertically simple but not horizontally simple. Why? Because vertically simple it's fine. Why? Because vertically simple means what? It should be x is fixed, the x should run from this to this, and y should run from some curve to. So that means this is fine. This is one. It is vertically simple, but it is not horizontally simple. Why? Because y varies from where to where. So this is my y range, right? This is my y. So y varies from this to this. But if y varies from this to this, so there is no fixed curve. Like if y, what it means? Horizontally simple means what? That means I have to fix y from some range, okay? But your x should varies from one curve to another curve. Fixed curve should be there. But you see, look at the region. So if y range of y from here to here, but x varies from where to where. From in the left hand side it varies from this curve to this curve, but if you go to the right hand side its curve changes. So therefore no fixed curve is there that is varies from one left hand side to another right hand side. So that is not fixed. So therefore it is actually vertically simple, but it is not horizontally simple. So horizontally simple means what? Horizontally simple means y should be keep fixed, right? Y should varies from some interval this. So in that case this is the range from varying of y. However, x should varies from h1y to h2y. So the left hand side you will have one function of y, right hand side you have another function of h2. But this time it is not the case, because y range is fine, but in between left hand side x varies from this to this. But if I come in the right hand side in its origin it changes. So therefore it is not horizontally simple. Similarly, these things also, this is horizontally simple, but it is not vertically simple. Horizontally simple it is perfectly alright, because y varies from this to this is the y fixed, okay, and it x should vary. So x should vary, right? X should vary from where? h1y to h2y. This is horizontally simple, right? And that is perfectly alright, because if y varies from this to this, then x varies from h1y to h2y. So if I say horizontally simple, right? Horizontally simple means yes. So y varies from c to d, x varies from function of y to h1y to h2y. So that means x is varies from this to this. And if I go down, that means it varies from this to this. So that means it is horizontally simple, but it is not vertically simple. Vertically simple means what? You have to keep x variable fixed. Now what is the range of x? So this is the range of x, right? Up to this. Then y should vary, x is fixed, y should vary some function of x to some function of x fixed. But in this region, in the above you will have this one function of x to another, and the same x it is a different one. So therefore it is not vertically simple. Okay. So therefore this is example of the left hand side is vertically simple but not horizontally simple, and this one is horizontally simple but not vertically simple. Now if I combine together, so this is the region you will have what is called neither vertically simple nor horizontally simple. Again, like the argument I have given, so there is a hole is there, so even x and y you will have a varying, but to have that it is horizontally simple or vertically simple. So like as I said, vertically simple is okay, but it is not horizontally simple or vertically simple, because it is not horizontally simple. Like horizontally simple means what? That means y is fixed, that means y range is fixed, okay. So x should be vary from one curve of y to another curve of y, but now it is differs from, if I in the left hand side it varies from here to here, and right hand side it changes. And similarly if I have x fixed, in the upper half you will have this to this, and the lower half this to this. So this changes. So therefore it is neither vertically simple nor horizontally simple. However, you will see I can break my domains. If I have a region, I can break it into many simple region. I think that I have given. Yeah. So some non-simple region that can be divided into union of simple regions. For example, this kind of region. So you can break it, like for this is the breakup. This is one. This is another. So this is one. You can have it, this is one, you can have it, this one. Now these are like, even if it is non-simple, but I can break up into finitely many pieces, each of them is a simple region. Similarly, you have another region. So suppose this is the whole is a non-simple region. However, I can break up into this one region, okay. This is another region, this is another region, this is another. So therefore you can break your non-simple region into finitely many simple region, and then you may ask, okay, can I calculate the what is called double integral and iterated integral. Okay. So, let me see at least for the vertically simple region how to calculate double integral or iterated integral. Okay. So, now Fubini's theorem for vertically simple region. Now, already you are familiar with what sort of domain or region I am saying that it is vertically. That means it is x is fixed, that means x varies from a to b, and y should varies from some curve g1x to g2x, where g1x is lesser or equal to g2x and g1 g2 are continuous. So, that is exactly I have written. So, let or suppose if f is a function from R which is a vertically region or type 1 region, and suppose it is continuous on this region. So, that means double integral exists, and also iterated integral exists, where R is like that and g1 g2 are two continuous functions satisfying these properties. Then this theorem says that the double integral over this region R, which is actually vertically simple or type 1 region, which is nothing but the corresponding iterated integral. So, what I am doing, again it is very nice. What I am doing is that I am performing with respect to y integral first. That means I am keeping my x fixed. Now, if I fixed one x, okay, then y varies from where to where? Y varies from g1x to g2x, right, vertically. So, if I fixed x here, that means y starts from where? This is the first point it should start, that means g1x, that means bottom curve, and where it will end, it is the g2x. So, that means this is the line. So, that means what will happen, you fixed x, think about or you have to integrate the functions with respect to y variable, but this time y is varying from g1x. So, that means it varies from variable kind of, if x is changing, corresponding the variable also changes. Earlier it will happen when I talked about what is called bounded rectangular region, these are the constant actually, but this time now it is a function of x. Okay. So, therefore, keeping x is fixed, you just draw a vertical line, it will hit the corresponding g1 and g2x into 2 points. So, bottom one is the curve associated with g1 and the top one is the curve associated with g2. So, that means you integrate from y g1x to g2x, integrating the function f of x comma y, keeping x fixed, okay. g1x it will give you some value, g2x will give you some value, you have to perform the integration with respect to y variable, and for each fixed x it will give a function of x, and you perform the, and then you perform the integral with respect to x variable. So, that is how you can calculate for that vertically simple region the kind of double integral. You can calculate in terms of the iterated integral. So, it is expected. So, now since x is varying from a to b, so that means you have to first perform your what is called y integral. That means you first perform your integral of the functions f of x y, keeping x variable fixed with respect to y variable, because y is varying from g1x to g2x. Then this will give you a function of x, and you perform the integral with respect to x. So, that means if I have a vertically simple domain, so first you perform the y integral and then you perform the x integral, because the variable y it varies from one function of x left hand side g1x to g2x. Therefore, it is natural to perform the y variable integration first and then perform the x integral, and this will give you the double integral of f over that vertically simple region of the functions f. Okay. Okay, so that is exactly I have written whatever I just said, finding integral limits or vertically simple region. What I am saying is that I actually draw a picture. So, innermost integral means actually this is the integral called innermost integral, this is innermost, okay, innermost integral. What I am saying is that, okay, so innermost integral is what with respect to the variable y, okay. So, that means you have to perform the integral with respect to variable y. Now, what we have to do, draw a vertical strip or arrow headed line parallel to y axis. So, this is the line, okay, this is the one. So, this is the line, it is parallel to y axis, right, over the region R. Then what is y limits? Where the vertical strip enters the region, that means the bottom curve. So, this is the first entry point for this vertical line, this is the entry point, okay. So, bottom curve of the region R, okay, that is the y limit. So, that means you have a fixed x, you have a vertical line parallel to y axis, it will hit one or it will enter the region by hitting the bottom curve, right, that is exactly I have written. So, where the vertical strip enters the region, that means the bottom curve of the region R, and where the vertical strip leaves the region, that means the top curve of the region, okay. So, that means you draw fixed x, okay, that is the fixed x, draw a line, it hit it here, that means enter the region in the bottom curve and then leave it here in the top curve, okay. So, this is the called y limits, and what will be the x limits? Then you just vary your vertical line from this direction to this directions. Okay. So, this direction to this direction should vary. Now, this is again one vertical line, one vertical line, then it will cover the full region, full your vertically simple region, right. So, that is the x limits. Slide the vertical strip over the region R from left to the right, while vertical strip is sliding over the region R. What is the starting value of x? So, this is the starting value of x is equal to a, because this is the vertical line. Okay. Then you parallelly shift to the right end, and that ends here at the point B. So, therefore, the leftmost value of x is nothing but a in this picture, and what is the ending value of x is the rightmost value of x, that means this is the B. Okay. So, that exactly I have explained, this is the object I have explained. So, this is the innermost integral, that means you perform the integral with respect to y variable. So, that means for fixed x, draw a vertical line parallel to y axis. It enters the region by cutting the curve g1x, it enters, that means g1 of x is the what is called entering point, and then it leaves the region by cutting your curve g2x. So, that means that it is leaving the point. Okay. Then your y limits should be actually what? You have to perform the integral keeping x fixed, and limit should be g1x to g2x, because it is entering in the region at g1 of x, leaving the region at g2 of x. And then what you have to do? You have to perform the x limit. X limit means perform the x integral. Then you just shift your vertical line from left to right, and left vertical line it is starting at the point x is equal to a, and right one is the left the region what is called vertical line, which at the point x is equal to b. So, limit should be x from a to b, and that exactly you have to perform the iterated integral, and which will give you the what is called the double integral, value of the double integral. One example, it will be more clear. Okay. Suppose your region R is like that, is the xy is in R2, x is running from 0 to 1, and y is running from two curves, say y is greater equal to x q and lesser equal to x. Okay. Again, x q and x both are continuous functions, x q is lesser equal to x, for this x lies between 0 to 1. So, everything very nice. So, your R is vertically simple region. Your function is again it is a polynomial in x. So, therefore, it is a continuous function. So, therefore, by earlier Fubini's theorem it says that you can calculate your double integral over this vertically simple region by computing your what is called iterated integral. Okay. So, this is the double integral I want to calculate. So, what you have to do? You have to do first perform the integral with respect to y variable, and then perform the x. So, this is your function f of x y, keep as it is. I have to perform the integral with respect to y variable. Now, this time, since as I said the vertical region, the entering in the region it cuts the point x q, and leaving the region it cuts the point x. So, therefore, limit should be y from x q to x, and of course, x you have to vary the vertical line. Left vertical line is x is equal to 0, right one is x is equal to 1. So, therefore, this is the integral you have to calculate, and which will give you by Fubini's theorem I have discussed in my last slides exactly the value of the double integral, and that integral you can easily calculate, right. You have to perform the integral with respect to y, keeping x is fixed. Okay. So, what will happen? This will come outside x minus 1, and you have to just perform dy, that means y, and you have to take the value x minus x q, it will be there. Okay. Keeping x is fixed, right, x is fixed, you have to perform the y integral. So, that is okay, and then you perform the integral with respect to dx, and that is the Riemann integral in the single variable case. You know, you perform it, you will be able to find the value 13 by 60. Okay. So, for this vertical simple region, again you can calculate the double integral by performing or by evaluating what is called iterated integral. Okay. This is another region. This time I am kind of having horizontally what is called simple region, not vertically simple, because this time x is fixed and y varies. Earlier what will happen? Earlier, oh, I think this is x fixed, or this is also vertically simple region, sorry. This is also x is fixed, y varies, right. So, x is yeah. So, this is also vertically simple. So, this is also, so x is fixed. So, vertically simple region. So, x running from minus 2 to 1, and y is running from 0 to 1 minus x. Again, this is a continuous function 0, this is a continuous functions. 0 is lesser equal to 1 minus x in this region, that is perfectly all right. Your functions f of x y is a polynomial in y, which is a continuous functions. Therefore, Fubini's theorem can be applicable. And by Fubini's theorem says that your double integral is nothing but this the corresponding iterated integral. Okay. You perform that. So, that means I want to calculate this double integral, this is the double integral. So, what you have to do? You just first perform the integral with respect to y variable first, keeping x is fixed, and then perform the integral with respect to x variable. So, your function is 4 minus 1, I have to perform the integral with respect to y, that one is perfectly all right, provided you have to be careful, because since I am in vertically simple region, y should vary from, so if I have to draw a vertical line, it should enter the region by cutting the curve y is 0 first, or that means it should y is equal to 0, and leaving the region at 1 minus x, that means it should be 1 minus x. And this is your function, so you have to perform the integral with respect to y variable. Since it is a function of y, you have to just calculate the definite integral, varies from y from 0 to 1 minus x. It will give you a function of x, and your x varies from minus 2 to 1, because at x is equal to minus 2, it is the left vertical line, and then from left to right, you have to cover the full region and you have to leave. So x is equal to 1, it is the right vertical line, and you have to perform what is called your iterated integral. If you do that, you just do the simple calculations, you will be able to conclude that the exact calculus or value of this double integral is 27 by 2. Okay. So, therefore, if you see, if I give some problem and say that calculate the double integral or Riemann integral or Riemann-Darboux integral, you have to just look at the domain first. Okay. So, if you see the domain, of course, if it is like bounded rectangular region and suppose you somehow prove that your function is continuous, then of course by Fubini's theorem you just calculate one of the iterated integral, and you will be able to solve your what is called the value of the double integral. However, if your domain is not like bounded rectangular region, it is like of like type 1, type 2 or vertically simple or horizontally simple, by looking at the domain if you see, then again if you somehow prove that your function is nice, that means continuous functions, and suppose if you say that okay, it is of either vertically simple or say horizontally simple, then you just perform one of the iterated integral. So, for vertically simple you perform the y integral first and then do the x integral, and it is expected because of the symmetry, if you are in the horizontally simple domain, then you have to perform the what is called x integral first. That means you have to first perform the integral with respect to x variable and then do the integral or perform the integral with respect to y variable. Okay. So, I think that is I am going to explain. Yes, Fubini's theorem for horizontally simple regions. Again, horizontally simple regions means what? Y fixed, means y is varies from C to D, y is fixed. Okay. X varies from one curve to another curve. So, the x varies from h1y to h2y. So, this is called horizontally simple. Okay. So, let me just see the statement of the theorem. So, suppose you have a functions f from say horizontally simple region R, and you know, so what is the horizontally simple region? That means in this case y is fixed, varies from C to D, however x varies from one curve to another curve h1y to h2y, with the fact that h1 h2 are continuous and they satisfies this condition h1y is less or equal to h2y. If this is my case and if my function is continuous, okay, so that means double integral and iterated integral exist, then it says that the value of the double integral is exactly equal to this iterated integral. This time what we have to do, again it follows from the region, that means again I have to first perform the what is called x integral, that means the integral with respect to x variable keeping y variable fixed, and then you have to perform the y integral. Now, once I am fixing x and fixing y, perform the integral with respect to x, then you have to careful the limit from x. So, again as I said, like in the vertically simple domain, you will see I have already written. So, that means you have to draw a what is called a line which is parallel to x axis, and then you have to see for fixed y it enters the region at h1 of y and then it leaves the region at h2 of y. So, that means the value of x should be h1y to h2y. Okay. And there you have to perform the x integral first and then you have to perform the y integral. I think I have written here. Okay. So, I think I have written, yes, look, so finding the integral limits for horizontally simple regions. Okay. Look, so this is the horizontally simple region. Okay. Like in the vertically simple region, for fixed y you draw a line which is parallel to x axis, then it cuts or enters the region at h1 of y and it leaves the region at h2 of y. So, I mean innermost integral, that means this is the integral I am talking about, this is the innermost integral. Okay. So, innermost integral is what with respect to the variable, that means with respect to the variable x, or perform the integral with respect to the variable x first. Okay. Draw a horizontal strip or arrowhead line parallel to x axis over the region R. Then you have to perform the x integral, that means x limits. So, where the horizontal strip enters the region. So, this horizontal strip enters the region at this point, right. So, that means leftmost or bottom curve of the region R. So, this is the leftmost curve, this is the leftmost. Okay. And where the horizontal strip leaves the region, that is the rightmost curve, that means the h2y. And then what we have to do, then you have to perform the x y limits, that means you have to come from this way, That means you have to come either from C to D or D to C. I think C to D is better. Okay, that one. So that means, so first you have to draw a horizontal line and then you vary to cover the full region. So that means it starts from this horizontal line at the point C and it leaves the region at the point D. So here I have written slide the horizontal strip. So you have a horizontal strip over the region R from bottom to top. So that means this is the bottom and go to the top. So if you do that one, so that means if you cover your whole region, this horizontal line from bottom to top, then it will be a value. What will be value? So at the bottom one, it will give you the value C, and at the leaving that region at y is equal to D. So that means that's exactly I have written what is the starting value of y, that is bottommost or lowest value of y, and what is the ending value, it is the topmost or highest value of y. So if you do that one, then you cover the full region, and that's how you have to perform the iterated integral, and that will give you the value of the double integral. Let me see, I have one example I should talk about, then I should finish by just explaining this example. So take the example, same example, okay, the function is same like this one. But this time again I am varying, I am actually what is called horizontally simple region. That means this time y is fixed, x is varies. Okay. So consider this domain, collection of all those x, y in R2, y varies from 0 to 3, but this time x varies. In the left hand side it is -2 and right hand side is a function of y. Of course this is also a function of y, you can think about it is a constant functions, and it satisfies -2 is less or equal to 1 minus y over the region this one. So therefore it is a horizontally simple region. Now you have to calculate this double integral. Now you just apply your Fubini's theorem, because this function is continuous functions, right. So you perform the x integral first and then you perform the y integral, because y is varies from fixed interval 0 to 3. That will give you some hint. That means I have to first perform, keeping y variable fixed, x integral I have to first perform, and then I have to perform y integral. That's the hints you have to, it is given at least in the domain. By just looking at the domain, whenever you will see some x or y variable fixed, you do that integral in the later one. So first you perform the x integral first and then do the y integral, because y is fixed, varies from 0 to 3. So here, okay, so by the earlier Fubini's theorem, it says that this is my function f of x y. I have to perform x integral first, but you have to be careful in the limit, because at x is equal to -2, it is entering the region. Okay, so that means I have a horizontal line, it is entering the region at x is equal to -2, and at x is equal to 1 minus y, it is leaving the region, because this is the horizontal strip. And then you have to vary your horizontal line from bottom to top. So that means from at y is equal to 0, you have a bottom horizontal line, and y is equal to 3, you have a top horizontal line, and you perform this iterated integral. So now of course I am performing with respect to x variable, keeping 4 minus y, that means y variable constant, that means 4 minus y will come out. You have to perform the x integral, that means dx, again value is 1 minus y minus 2, that means it will give you minus of -2 means 2, that means 3 minus y, and you just perform the y integral. Okay. So therefore if you do that one, then you will be able to calculate what is called your double integral. Okay. So therefore what I have done, so I have just discussed two domain I should say. One is vertically simple and another is horizontally simple. And vertically simple means your x is fixed, y varies from one curve to another curve. Horizontally simple means your y is fixed, x varies from one curve to another curve. And Fubini's theorem says that if my function is nice, that means continuous functions, that means all the iterated integral and double integral exist, then performing the or calculating the iterated integral, you can calculate your double integral. But when you do the iterated integral, it is quite clear from the definition of the domain that which integral you have to do first and which integral you have to do second. So for example, vertically simple, since x is fixed and y varies, that means you have to first y integral first, and then you have to do the integral in the second one is the x integral. When I am in the horizontally simple domain, that means since y is fixed, and fixed means varies in the fixed interval, and x varies from some function of y to some function of another function of y, then it is expected I should perform the what is called x integral first. Okay, keeping that limit should be the function of y to function of y, and then I have to perform the next integral by y variable. If I do that, then I will be able to conclude what is called or calculate the double integral. So this is for very simple domain. For this kind of domains, there is a way you can calculate your iterated integral and you can evaluate your double integral. So there are many ways you can do that. This is one of the ways. So maybe in the next lecture I will talk about, again, if I have some domain, you can break it into many simple domains like this kind of domains, and you will be able to calculate the double integral by calculating or by evaluating what is called iterated integral. I think I should stop here. So, in my next lecture I will talk about what is called change of variables and couple of applications of my double integral. I think I should stop. Thank you.